Great. Okay, so ladies and gentlemen, we are open for business. Maybe I'll ask someone. Yeah, maybe you could, if someone could by the door get the lights. Gosh, still kind of faint. But okay, so I prepared a sample exam for today. I also prepared a set of slides, which I could go through, which hit on some of what I consider important parts of this course. But my foremost priority for today is to address questions that any of you may bring here. And following that, we could certainly go to the additional slides and more comprehensive coverage of the final exam sample questions. But let me start out by asking who would like to bring some questions forward for me to answer about any of the materials? Or would you prefer me to talk a little bit in high level about what to expect on the exam as a whole? Okay, that seems to be interest in that. Okay, so I'll only spend 2 or 3 minutes on this, but basically the final exam is going to consist of a set of questions of varied sorts. And there's basically going to be three or four sort of major types of questions on the exam, okay? The shortest, I'll go in sort of level of work involved and level of extent to the answer required. The first of them is a set of true-false questions. Okay. Now, it is very important when you fill out the true-false questions to try to put down your reasoning. Okay, because if you answer wrong to the, whether it's true or false, me understanding your reasoning may allow me to still give full marks, because sometimes a student reads into those sort of questions a deeper level of questioning than I intended. And by explaining and alerting me to it, I can give you at least partial credit often, and sometimes full credit. Okay, so that's type 1. Type 2 questions will be fill-in-the-blank questions. These are questions where you're going to put in a phrase or or an indication. Now, for those sort of questions, in the interest of sort of quizmanship, it's valuable to note that I'm not seeking to exhaustively test your understanding of the particular name. I'm not going to be obsessed that you got the name wrong. So for example, if there's a question where the answer is a ring lattice network, and you put down something like a loop lattice network or a ring network, I'm gonna be inclined to give you a very large fraction of the marks, if not all of the marks. So don't get caught up in remembering the exact name, although it's great if you do. What is important is to communicate that you know something about what's being said if you're unsure of the name. So, if you know it, boom, just put it down and you're done. If you don't, put down something that indicates that you're familiar with it and these are the features, even though you can't recall the name or the exact phrase to use, okay? So those are fill-in-the-blank type of questions. A third type of question is a type that you're going to be asked to put down some reasoning. And here it'll typically be a couple sentences that I'm looking for. Often it will be questions like list 3 disadvantages of X, or 3 advantages of this, or list at least 3 types of network supported that we talked about in the course of the semester, or something like that. So you're being asked to list out things. Now, for this type of question, more so than the previous two, there's a risk that you might run out of space. Maybe you start putting something down and you realize, wait a minute, I'm off, and you want to cross it out and put down more. You can go to the other side of the sheet, but just indicate, answer on, back of sheet or something like that. Answer on reverse to alert me to that. Those sort of questions, I'm not looking for an essay. I'm just looking for some understanding, of fewer than 5 sentences typically, that could provide a response. If I ask for 3 and you put down 4, and one of them happens to be off base, I will still give you full credit, so it doesn't hurt to put down extras. Within reason. If you put down 100, random buzzwords from the term or something, and you just hope, that 2 of them are in there somewhere, I'll be less charitable. But if you put down 5 and I think only 3 of them are germane, and I've asked for just 3, I'm going to give you full credit. Okay. So I would encourage that, but don't feel like you gotta put down more. Okay, the final type of question, this 4th type of question, is going to be more extensive in its answer. It's going to take longer. It is going to be potentially more tricky, and it will be commensurately receive a higher number of marks. Okay, and there are 2 questions on the sample exam. You see me, 2 pairs of questions which I put down of this sort. These type of questions involve sometimes mathematical derivations or writing down a set of equations carefully, solving something. These types of questions. Now, once again, if you're welcome to go to the back of that sheet or other sheets for that matter, but if you do so, alert me. There's no shame in crossing things out. So basically, I'm going to be looking for a couple of things for these sort of questions, okay? So the first thing is, if you go through and you solve it and you get the answer with a capital T and a capital A, I will check that, and if you have reached that point, I will award you full marks. Okay? If you don't reach that point, or if you're not sure if you've reached that point, you may have made a mistake along the way. That's where there's more significant lines of advice I could give. Number 1, most important thing I'm going to be looking for is, do you know roughly what's going on? Okay. Do you know roughly what you're doing? And so if you say up front, I'm going to try to solve this problem, you don't have to use those words exactly, but I am going to do the following: step 1, do this; step 2, do this; step 3, try to do this. That will often give you a large fraction of the marks, like half right there. Because okay, so this person knew basically what was going on, but they got lost in the algebra, or they got lost in some particular detail, and I can often give half the marks there. Okay? Basically, I could tell, okay, this person isn't just flailing around and, wriggling and trying to make it seem like they're going somewhere, but they're actually just confused. And believe me, I see my share of wriggling and flailing around. So that's the most important thing. If you know basically what you got to do, communicate it. Now, if you get partially through it and then you stop That's also very good. And I will try to reward, a large fraction of the marks for that. So if you get, 3/4 of the way through a derivation and bogs down and you don't have time to finish it, I may be able to give 3/4 of the marks for that. So that's a good thing. It's by no means binary, so by no means all or nothing. And I'll be looking for evidence, basically where you're going, and I'm very sympathetic to people making a mistake in a derivation. Now, if you don't feel you've solved it, but you've noted some things, like you have some answer, but you think it's wrong. It can't be the case for some reason. It doesn't make sense. Tell me, and I'll be more inclined to say, okay, this person is fairly savvy about these things. They may not have gotten to the final answer, but at least they've spotted that the answer they gave has a problem, and they know where they need to go. I would give a very large fraction of the marks for that. So basically, communicate to me you know what you're doing, and you're not flailing. You know where you're trying to go, and you have a sense of whether you've gotten there or not. Say I don't have time to solve for the other equilibrium or something like that, but I know there is one. That will be a really welcome thing. So those sort of questions are going to take the most time. And what's pretty important is to realize that the exam is not exactly going to be death by 1,000 cuts, but not even by 100. But there's going to be a fair number of questions on it. Okay, I'm placing it around 60, 61 questions is my recollection. Okay, and what that means is you don't want to get bogged down in one question at the expense of the others. Those bigger questions, they're going to have a bigger share of marks, but as a fraction of the whole exam, they're still pretty smaller amount. So, be sure to hit those small questions, the fill in the blanks, true and falses, the couple sentences. Before you just wail at these big ugly questions. So that would be my advice on those 4 types of questions. Pace yourself, and I try to indicate you know what you're doing. Any other questions or sort of issues that I can point out about the exam? You won't need a calculator. If you're solving things algebraically, and a certain term keeps on coming up a lot. So, you have, alpha plus 1 over tau or something like that. If that appears lots of places, you might give it a name. You might give it the name, D or something like that. And just substitute every time this would occur, do this. And then when you need it re-expanded to this, you can do so. But meanwhile, you're operating with smaller numbers of things. You don't have to write as much. So if there's a big string of these things, you want to just give them a name collectively. That's a good thing to do. You can feel free to tell me if you have a particular term like 1 over tau that you see a lot, and you want to turn it into a different term, call it C, or call it Z. If you want to turn that into Z, that's fine. Just tell that to me, and use that instead. Just be sure. So if you see, Z times tau, there's a simplification opportunity here. So at some point you want to be thinking, what is this? How is this defined in terms of tau? So you can simplify things. But other than that, it's good to give names to things. It will simplify the amount of work that you have to do, and you'll see those same patterns appearing over and over again. I guess one other thing on the long problems, I prefer to see each step. So if you can jump ahead 3 steps at a time, that's all well and good, but I can actually give you more credit if I see each step along the way, because if you mess up at one point, I can give you full credit for everything before that. So show me the steps along the way if possible. I would welcome that. I wouldn't critique that. Okay. So this is some comments in the exam. This I was pretty happy with the sample exam, how it came out. I think it's pretty comparable, just a bit shorter than the full exam. Okay, but similar kind of mix of sets of questions, sets of topics. Pretty similar mix. Okay. Anyway, enough of me talking without questions. So, what could I start by answering? Anyone have questions like on broad coverage? Are we responsible for X? Yeah.
I have a question on stable equilibrium.
Yeah.
So, for example, we know, like in the gopher coyote one, it's kind of like it has like a circular.
Yeah.
Is that considered a stable like equilibrium?
This is a great question. This is a great question. So, I didn't really want to confuse you that much, although it's a fun factoid. Okay, and I still don't want to confuse you, but I'll say it anyway. Okay, since you've asked a really good question. So this is going at a technical level. What's going on here in state space is that there's actually a fixed point. There's a point where nothing is changing, where the derivatives, the d gophers dt, and the d gophers dt and the d coyotes dt, where these things are what at this fixed point? They would be zero. And what's going on here is that it's actually going around that. Okay, so it's what's called technically a limit cycle. So it's actually going around it, and so it could be here, it could be here, it could be here, and it goes around and it completes the cycle around this point. If you were to magically set it to be right here, it'll be completely stable. Okay. Nonetheless, this is sometimes called, I think someone informally did, and again, I'm cautious about saying this, a dynamic equilibrium. Okay. Now, the reason I'm cautious about saying this is because you have to be very, very concerned. When people say equilibrium, normally it means stasis. There's nothing changing. It's not going up or down. And this does not match that criteria, but it's stable in the sense, it's an equilibrium in the sense that it rests there. There's activity going on, but of a very defined, repeatable sort. And so this is sometimes called the dynamic equilibrium, and it just sort of cycles around there. It's not going anywhere. It's not wandering anywhere else. It's just staying in the same area of space. This is an example, Jordan, of a question where, like, if a student said, if I said true or false, an equilibrium is the same as a fixed point. And if you said something like, well, no, actually, fixed point is zero change, and an equilibrium can include dynamic equilibrium, I'd say, okay, full marks for Jordan. Great. He took it at a more sophisticated level than I meant for people to take it. But whether this is an equilibrium, it's a little bit of a definitional issue. I'd prefer to say it's not, but to say that it's kind of you could say it's a related concept that allows for still repeated behavior. Is that helpful?
Yeah.
Yeah. Okay. And these sort of things are quite common. There's around fixed points, that's one sort of behavior. Another sort of behavior that you'll see, which we've seen many times in class, is where it spirals in and approaches it. Another sort of behavior is where the fixed point will kind of be shooting out this way and sucking things in this way. And it kind of squirts it out that way. It's not always accompanied by that sound, but It's always good when it is, I think. So this is one type of another type would be they're all sucking in. Ross Perot even used that in a debate a long time ago, maybe before you folks were born. So it's sucking in, or another type where it's pushing out along the way. This is called, when it's sucking it in, whether in a spiral form or in this sort of form, we term it a stable equilibrium. It's stable. Why is it stable? There's no horses involved, but
you can change the values a little bit and it'll still go back to that.
Yeah, we could sort of knock it off from here a little bit. We could perturb it. We could do something to disturb it, and it'll be sucked back to that point. It'll resist change. It'll push back against change. Whereas if we're in a situation, where it's something like this, to be clear here, this is an equilibrium. It's not changing there. This is called metastable. Okay, you're not responsible for that term, but you really wow me if you use that. Put down your name as metastable or something. That's pretty impressive. So this is actually an equilibrium, but it's an unstable one. An example would be, okay, no, I don't want to do that. I've broken one.
The gopher or coyote one was like that.
Yeah, that's right. Like this is, okay, you folks could do it better than me. But this is like a metastable equilibrium, and if I don't try to adjust for it, there, right? So if it goes off, it'll accelerate off of it. It's in perfect balance here, but if you knock it off a bit, it will become unstable and zoom out. Okay, this would also be considered unstable because if you knock it off, it will in this direction. But this has kind of an interesting saddle type sort of geometry. But in any case, these are all the fixed points at the center here where there's no change whatsoever, and the question is how does it behave in the area right around it? So if I disturb it from this point, does it suck it back? So we have unstable and stable, and we don't have time to go into it in this class. But I think at one point in your careers, all you folks took the linear algebra course. And did you learn about eigenvectors and eigenvalues? Yeah. So it turns out what distinguishes these type of equilibria is the eigenvectors and eigenvalues. If you have an eigenvalue that includes an imaginary component, it's complex and includes an imaginary component, you'll be getting the spirals around. If it's only real components, it can be that are negative, it'll be sucking it in. If some of the eigenvalues are positive and some are negative, you can get this sort of situation. The ones in the negative direction and the eigenvectors in those directions, in certain directions, it's sucking in. Associated with the negative eigenvalues and the positive eigenvalues, it's pushing out. But you're not responsible for any of that in the class. It's just you got to realize that linear algebra has beautiful geometric implications, and it allows you to solve for these things, and that's what allows you to distinguish these type of fixed points. Okay. Yeah.
Just one quick.
Yeah.
So if it's like orbiting, say that fixed point,
yeah.
Do we consider that stable? Because like you can knock it around, but it's still like following that.
That's a good question. So this is a case where it's going to have only imaginary components in the eigenvalues, okay? So there's no real component, meaning it doesn't squirt out or suck in along any of these directions. So I would call it, is it stable? No, it doesn't suck it back in. Is it repulsive? No. In fact, it's quite beautiful. But it is in fact something right on the balance between stable and unstable. It's kind of right at that point where, in fact, it's neither sucking out nor pulling back in. And so, I wouldn't ask you to sort of say, okay, is it unstable or is it stable, and give you only two answers and expect you to come up.
Not the fixed point. I'm not
Yeah.
talking about.
Oh,
the
you're
fixed
talking
point.
about this thing.
Yeah, I'm
Yeah,
talking
the
about
trajectory.
Like, say it's like
Well,
on like a kind of orbit.
yeah, I mean, if you knock it off the trajectory, what's going to happen is it'll come out to another trajectory. We can sort of loop around.
In the gopher one, doesn't it?
Yeah.
Like
Come
it
back,
stays-
exactly.
It kind of like it's the inside's like forcing it out, but the outside's forcing it in. It's like if you add it, kind of like.
Oh, I see. So you're saying it actually may go like it may sort of remerge with the trajectory.
Yeah.
Yeah, you could be right about that. I'm actually thinking I've probably been a little bit misleading because the more typical case here is where you're right, that there may be a trajectory here around this, but the inner ones go out to it and the outer ones come into it, if that's what you're kind of talking about, yeah. So you can have that where basically these ones come into this dynamic trajectory around. You can have that sort of situation, and you may be right that one falls in that category. Okay, other questions though? Good.
So in terms of on the sample here,
Yeah.
the question of kind of around that is how many equilibrium points?
Yeah.
So would that be 2 then?
Yeah, 2. The reason it's 2. What are the 2 equilibria associated with the gopher case?
There would be a fixed point like you have on the board there.
Yeah.
It would be 0 and 0. for
That's
the two
correct.
stocks.
Yeah, that's exactly it. And ladies and gentlemen, the thing to avoid with those questions about number of equilibria, etc., is avoid getting stuck in the situation where you're only imagining kind of the typical case, which is, there's some gophers and some gophers and some coyotes, some gophers and some coyotes. Rather, you should be thinking also about the case where gophers and coyotes are 0. There's no growth in either one because there's no gophers or coyotes around, okay? So, in general, there's going to be one where you have gophers and coyotes together and one without gophers or coyotes, okay? Those are the 2 cases. And you'll see a very similar thing with infectious disease models where one equilibrium will be associated with no infection at all in the population, and one equilibrium will be associated with infection in the population where it's completely imbalanced, where all the flows are non-zero but equal each other. Often when we have the one with no infection at all the flows are what? 0. When we have the one where there's an endemic equilibrium, where there's infection in the population, the flows are non-zero, but they're all equal. So the flow into infective is the same as the flow out of infective. In other words, rate of recoveries equals rate of new infections. Okay? Yeah. Question?
So that means you only have 2 cases for equilibrium
No.
at one time?
Not in general. No, not in general, but for the models that I gave as samples on this exam, for this guy here and for this guy here, there are 2 equilibria. Okay, you can get in situations where there are more than 2 equilibria, like there's a whole family of equilibrium, even with 2 state variables for certain types of systems. And you can get in a situation where if you have more state variables, like you have SEIR, you might have additional equilibria as well. So in general, the number of equilibria will rise as the number of state variables, as the number of stocks rise, okay? The number of equilibria will rise. And in some cases, those equilibria will be competing in terms of stability. So you'll get something like a situation where disease-free, case where no disease, that's stable and things kind of go into there. So if this is susceptible, maybe this is stable. But then there'll also be another equilibrium which is stable out here, and there'll be a line between them, and these are called basins of attraction. And so anything here may come down and it kind of goes into this. So if we start here, it'll go into here. If we start up here, it'll come into here. If we start over here, it will come into here. But meanwhile, up here, it would be sucked into this equilibrium. I mean, the geometry will differ for a case. So here are two different so-called basins of attraction. You can almost think of this as like the Rocky Mountains. And if you put a drop of water on one side, it runs down to the Pacific. You put a drop of the water on the other side, it'll run down to Hudson Bay or whatever. It's a kind of similar situation. There'll be a line delineating them. So these are called basins of attraction. And in general, the more safe variables in the system, the more equilibria there will be, and the possibility rises that there'll be multiple stable equilibria like this. This sort of thing only comes up in nonlinear models. Okay, only in nonlinear models you get this sort of multiple basins of attraction in that sort of form. Okay, other questions? Anyone want me to solve some problems on that? Exam? Anyone have questions on sort of broad topics that I might or might not be covering?
There's one question. It's about individual gopher.
Oh yeah.
When
Yeah. You mean for interpreting this, right?
Yeah.
And I say, okay, from the perspective of a single gopher, what's going on there? And from the perspective of the gopher population as a whole, right? This is for the peak here, and roughly year 6 here. Okay, so here we go. Here's the gopher population up here. Okay, so what's going on at that peak?
for the population, the inflow equals outflow.
Population, the inflow equals outflow. That's right. What is it that's going on at the level of an individual gopher? Yeah.
Competition for resources is very intense, but there's very low predation.
Okay, so there's still low predation. That's right, but there is considerable competition for resources because you have a high population. But from the perspective of the gopher at a mathematical level, there's something very special going on here. If the population is no longer increasing nor decreasing, when that gopher dies, it's eaten by a coyote in this model, it's eaten by a coyote. How many gophers does it leave still living? Basically, it gives to the world exactly one gopher to replace itself by the time it dies. Okay, it's replaced by exactly one gopher. So it basically, on average, gives birth to one surviving gopher. And the analogy here is almost exact to the case of what from infectious disease models? What happens at the peak in the number of infectives in an infectious disease model? R star equals 1. And what does that mean? Sorry. I hear almost a Greek chorus, and that's a great chorus. So could someone amplify the chorus?
The infected person infects one other person like that.
Before they recover. Before they recover. So from the perspective of a single individual, they've replaced themselves with exactly one person who's sick by the time that they recover. That's why it's not going up or down. From the perspective of the whole model, of the aggregate, sort of the population as a whole, what's going on at that point where infectives is at a peak? What's sort of distinctive about that situation where infectives is no longer going up and down? This is not a trick question.
So now we're talking at the level
At the level of the whole population.
of simulation in general. So now we're saying, okay, so the derivative is 0.
And what does that mean in terms of the inflow and outflow?
That they're equal.
They're equal. So the number of people recovering per unit time has to equal the number of people getting infected per unit time. Okay? So from the perspective of the whole population, you could talk about flows being equal. From the perspective of a certain individual, it's about replacing themselves with one other individual who's infected by the time they get sick. Now, before that time, if we're thinking about an infective going up, before the time that it peaks out, what's the relationship between infection and recovery? When the number of infectives is still rising, that early time period, before it peaks, in this early time period, what's the case with infection and recovery?
Infection is greater than.
Yeah, it's greater than recovery. This inflow is greater than the outflow, so this is going up. Okay, good. From the perspective of a single individual, what's going on there?
They're infecting more than one person.
They're infecting more than one person, they recover. So over time, what limits that is the number of what? Or the fraction of people around them that are susceptible. As this rises, they get less and less efficient at infecting people on a per person basis. A given infective has to look around more and more to find someone who's not yet infected or hasn't yet been infected. And therefore, maybe at the very beginning part of the epidemic, you take something like measles, you infect, in many contexts, people have recorded something like 15 or 16 people infected by each person with measles if they're surrounded by people who are susceptible. What is that called?
Ooh, are we talking about the force of infection now?
No, it's actually called, so Jesse mentioned before R star, so-called effective, this is R0 or R naught, or there's different names for it, but it's the basic reproductive constant, basic reproductive number. This is this one in a very particular context where everyone else around has never been infected before. So for measles, this might be like 16. So I've got, I as the first person with measles, if I came into the room and none of you had ever gotten measles before, and none of you suppose had a measles shot, I might infect 16 of you before I recover. But as time goes on, more and more of the people around me will have gotten measles, so I won't be able to infect them. So if there's someone who got infected 2 weeks in, maybe only half the people around them are infected, so have never been infected. So they might only infect 8 people. And then, as that fraction of people who've been infected rises and rises and rises, each person is infecting fewer others before they recover, until at some point they're only infecting one person, one to replace themselves before they recover. That's when this infective is at a peak. And then it starts to decline. Why does it start to decline? Why does the number of infectives start to decline? It actually declines really quickly after that. What's going on?
It's no longer it doesn't efficiently infect people anymore.
Good. Okay, so from the perspective of one person, they're infecting fewer than one. Okay, that's useful. But what else is going on from the population level? If we think of it from the population level, why does this drop so quickly after this point?
The rate of recovery is higher than the rate of.
Okay, yeah, there's lots of people to recover. But precisely because infective is dropping so quickly, now what else is lower? Well, susceptibles is going down, because people are still getting infected, so that's dropping, and the number of infectives is dropping. That's what we're talking about. We're talking about this dropping. And the more this drops, what else drops with it? The rate of coming into here. So we've got a big group here. Recovery is coming out of that. A lot of people ready to recover. And as that number of infectives drops, as recovery goes on, the rate of infection also drops. And so here we have, and the number of susceptibles is going down still, because people are still being infected. So you have this kind of situation where, you know, you have a very rapid drop, because susceptibles is going down, infectives is going down as well, and that leads to infections dropping very quickly, and you have a lot of people recovering for the infectives that are already there. So it drops very quickly. Okay, ladies and gentlemen, there's in a model like this, though, there's also some big important delays. Under what condition in a model like this would susceptible be going up? For this model, when is susceptible going up?
People start waning immunity.
Yeah, so waning of immunity equals what? Equals infection, right? So susceptible will be going up as long as waning of immunity here is greater than infection. It'll be going down as long as infection is greater than waning of immunity, right? And you'll note that also the number of susceptible may be rising even though infectives is still dropping. Why could that be? Why can infectives still drop even though number of susceptibles is rising? Yeah, the number of susceptibles isn't high enough. That's exactly it. So the number of susceptibles has to reach a certain fraction of the population to allow each infective to be efficient in the sense that they're infecting more than one person over the course of their illness. It could be rising, but it's still very low, and so the number of infectives is still dropping because they're still not they're still infecting fewer than one person per unit time.
Sorry.
Yeah.
In the case that you just said,
Yes.
isn't that at that point recovery rate is still greater than infection? That's why infectives still dropping then?
Because recovery is greater than infection
Yeah,
still at
that's
that
why
point.
it's still dropping.
That's right. It'll still be dropping, but from the perspective of a single person, susceptibles has to be high enough. A single person who's infected, susceptibles has to be high enough to make them infect at least one person before they recover. That's another way to view it. And what this means is until susceptible reaches a certain fraction of the population, infectives will still be dropping. It's not merely that it has to rise. No, it has to rise to a certain point. And in fact, that magic point that it has to rise to is the equilibrium point. Ultimately, it's the equilibrium is when what equals what. Equilibrium is when what's going on in that model here. Do I have a nice slide on this? Do I have a not nice slide? I've got to check. I don't even know if I have an ugly slide here on it. Hey, oh my gosh. Okay, yeah. Okay, yeah. So this is the dynamics here. Okay, I have something closely related, but so ladies and gentlemen, when we're dealing with a situation where, okay, let's go to this. When we're dealing with this situation, if we have a situation where we're in equilibrium, the whole thing's in equilibrium, and it's an equilibrium where disease is still established. What equals what? Inflow equals outflow for which stock? All stocks. All stocks. They all have no change. Rid of each equals 0, meaning the inflow equals the outflow. Everything here is in balance. Number of people infected per pick your time unit, week, equals number of people recovering per week, equals number of people who are waning immunity per week. And at that point, how many people get infected by an infected person before they recover? One person. One person. That's that magic point of balance where they're just replacing themselves, the population of infectives is not going up or down. And the population of susceptibles has just the right fraction of the population to make that happen. Because that's what limits how many people I can infect. Okay?
Sorry, is that unstable equilibrium then?
That's a stable equilibrium. That's a stable, well, for most for many models of infectious disease, that will be a stable equilibrium. It is possible that, if you have a model, if you have a situation where someone's recovery time is so short that the infection won't spread, basically what that means is that R0 is less than 1, in which case there will be no stable endemic equilibrium. It will not be stable at all, and you won't be able to get that stability. Normally, you're going to have some sort of stable endemic equilibrium associated with the presence of a disease, or in many cases you will, I should say, in which case you have all these three flows equaling each other, in which case you have a person who's infecting exactly one person but before they recover. But the goal of the public health system is to make this the case, to vaccinate enough people where even if someone were coming with measles into the Saskatoon airport, there might be quite a few people around who are susceptible, but the population as a whole is going to be resistant. We have what are called herd immunity, meaning that there's few enough people who are susceptible that the infection's going to be dying out. So they come in, they're going to infect fewer than one person before they recover on average. Because while there are individual susceptibles, they're rare enough that they're not going to be able to even infect one person before they recover. Okay?
So the Z-free equilibrium for that one is unstable.
Well, for the case where you have enough vaccination that this is the case, disease-free equilibrium, the so-called DFE is stable. So if this is the case, DFE is stable, meaning you could have occasional people fly into Saskatoon with measles, or with chickenpox, or with mumps, and it might infect one person, but that person is less likely to infect one person even, and so it'll peter out in the population. It'll die out. But meanwhile, the endemic equilibrium here will be unstable. Okay, it will be unstable. It would be repulsive. It would get sucked towards a disease-free equilibrium.
Okay, so I think you said. Did you say a minute ago? I think you said the endemic epidemic was also stable. Did he say that?
Did I say that?
Did he say that?
So,
I mean, it could be one. It could be either, right? It
Well,
kind of
okay,
depends,
if
right?
you have this, then this is the case. If you have this, then you have the DFE disease-free equilibrium is unstable, and you have the endemic being stable. These are the two basic
Really?
cases.
You have the endemic being stable,
You can absolutely have that, yeah. If you have this sort of situation.
but it could also be unstable. Could be either. I hate.
Yes, you could have it be unstable. You could have it be unstable and it goes into some sort of dynamic sort of cycle. You could in fact have that. So it repulses it away from there, and so it's never in stasis. So you could in fact have that. Generally speaking, for most models, you're going to have either this situation or this situation.
Right.
So it's either going to be the endemic is stable or the disease-free is stable. And what people try to do is to shift it from this to this.
Okay, so just one quick
Yeah.
question.
Yeah.
So in the case where R naught is less than 0 and we have a
Less than
disease-free
1.
equilibrium which is stable, less than 1 thing,
Yeah.
then there is no endemic equilibrium, is there?
There actually can be.
There can be, okay.
There
okay.
can be an endemic equilibrium where everything is zero, but it will be unstable. There can also be cases where it completely disappears. It does. There's not even equilibrium
Yes,
there.
okay.
There's no situation where it's completely in balance because of the nature of the system. But generally speaking, it'll exist, but it will be unstable. Okay. So there's two solutions. What that means is there's going to be two solutions to this in terms of two fixed points, but only one of them will be stable. Okay. Yeah. Other questions? Yeah.
How would that be in terms of R star? Because we would just talk about.
Okay. So great. So R star. So R0 is a very particular case. This is the case where someone's surrounded by others who have never been infected. Okay? And people differ a little bit. Sometimes they use it. They also include the case where you're surrounded by people who are vaccinated. They've just never been infected before. Some people will use it predominantly to talk about cases where you're surrounded by susceptibles. R star, so that's R naught. R0. How many people would I infect as a new infective in a population if I'm surrounded entirely by, and for the sake of this class, we'll just consider susceptible people. All right? I'm the first person who's infected there. Therefore, we call it a naive population. It's just like a tinderbox. And how many people do I infect? R star at the initial time will be R0 in a situation like that. But over time, as the infection spreads, those people who are infective will be surrounded by a larger and larger fraction of non-susceptible people, of people who have been infected before. And so R star would start at R0, it would drop. So that when half the population, it's very common that when half the population is infected, has been infected, R star might be half of R0. That's when I say that's common, there are models where that's not the case. So we actually tried one in class at one point where it takes longer people to get treatment, the more people are in line ahead of them, etc. And there it's not going to be quite as linear a relationship. But over time, so R star is measured at a particular point. R0 is measured, R star is measured at a certain point in time. You ask, how many people will an infective at that time infect before they recover? R0 is for a very particular case. For the case where they're surrounded by susceptibles. How many people would they infect? This is for the very special situation. R star is like right now, if we consider infective, how many people are they going to infect before they recover? That's the difference. Does that make sense? So if you happen to be in a situation right now where everyone's susceptible around, R star will equal R0. But over time, as more and more people get infected, have been infected, R star will drop. Okay? Yeah. Okay, good. Questions? Yes.
So I was looking at the question 5
Yeah.
in the same SIR model,
Yeah.
and you asked for the
State equation.
state equations.
Yeah.
So what I first did is, he wants the equations for the derivatives, which are
Yeah.
basically
That's correct. That's correct.
Okay.
That's all I'm asking for there.
Okay.
I'm asking you to translate that into state equations. And really what I'm talking about here, by the way, I'll provide you all these slides here, which incidentally expand on those from many you would have seen online last year. These include some that weren't there. So let's go see this. Where are we? Hey, no. I'm asking you to go from this to that. I wanna sense your ability to do that.
Yeah.
So I'm just asking you to write out things in this form within this question.
Okay, okay.
Yeah.
So, yeah, and so, okay, so what I did first is
Yeah.
I didn't do, yeah, I had it with, like you had it in the slide with the dot over top, so.
Yeah.
So it was that if I wanted to cancel things out, I would have nothing left. I just mean that I had the derivative of the stocks in the equation, so there was a positive value, and then minus something else.
Yeah,
Okay.
that's good. Although I think I think that's good. So you're saying you put the flow in and then the flow out.
Yeah, and what I also
Good.
thought, well, maybe that's okay. All right, now
Yeah.
and then that was kind of the lead up to, like maybe if we have time later, we could solve for an equilibrium that isn't the trivial equilibrium
Totally.
in that case.
Totally. Absolutely. Yep. Happy to do that. I also provided for this particular model some time ago. Okay, now I have to be careful here. No, okay.
You might have slides for it, actually.
I actually have. I provided to you.
Photos from the Blackboard?
Yeah, I did photos from the Blackboard and I posted those. I also did this. And I provided them too. So these in fact are exactly
Well, let's not do it here then.
the corresponding system here, where omega is the rate of recovery. This is kind of the standard reasoning. This C is the rate of contact. I over N is the fraction of people who are infective. So if I have contact with 100 people per day and half the population is infective, I have contact with 50 people per day who are infective. So that's C times I over N. And each of those confers 1% chance. I have about a 50% chance of that a given susceptible will get infective. That's what this whole term represents, right? And that's a flow out of here into there. Look, when you're writing down these equations, one of the tricks are, look, if you're in a situation where you have a flow, you should have a term for this flow. Whatever the value of this flow is, as long as it's flowing from one stock into another, this flow should have a negative term from the stock it comes out of and a term in for the stock it goes to. So this is the stock whence it comes, and this is the stock whither it goes. Similarly, this one here, I over tau, that's the flow from here to here, and it flows into R here. Okay, and this is the flow out of R. And notice, and this is very important here, folks. If you follow this derivation, one of the first things I do is I say, wait a minute. What do I say?
You say, I don't even need to worry about one of these.
I don't even need to worry. Why is that?
Because it'll just be the remainder.
It'll just be the remainder. The total population here is fixed. There's a total of N people in the model, and all we have to do is specify two of these, and we know what the other is. N is some number, 1,000. And so if we know susceptibles is 400 and infectives is 100, then we know recovered has to be the balance, 1,000 minus 400 minus 100 or 500 remaining. So we only have to deal with two of these, and then the fun begins. And here, critical. You're going to say, wait a minute. Okay. Two state variables. Generally, this is going to mean two solutions. And Rowan, when I said earlier, normally that means two equilibria, right? One's typically going to be stable, one's going to be unstable, or very commonly. Okay, so what we need to do here is we need to look for solutions. And often there will be kind of a trivial solution where we will say, okay, what about the case where we have a situation where there's no disease at all right? Then this is 0, this is 0, I is 0, this equals 0. And then okay, so if I is 0, this whole thing is 0. This guy is 0. And what's going to go on is that now we have S dot equals that. If S dot has to be 0 for us to be at equilibrium, then this whole thing equals 0, and that must mean S equals N. Okay? Now, I neglected, I stand remiss or sit remiss. Here, I should have emphasized the most important thing. Please communicate this to me. Please. I spend the better part of a week marking these exams. And it'll be a happy marking session for your exam. Even if you have trouble down below, just communicate. If you can get this far, and you can communicate, you want to solve for I and S, because those are the two variables on the left-hand side, such that what thing is the case? You're trying to solve this such that what is the case?
They're both 0.
Both are 0, because at that point the system is in balance. S dot means how fast is S going up or down? We want it to go neither up nor down. We want it to be exactly at rest. S dot equals 0. The rate of change of S is 0. The rate of change of I we want to be 0. We want to find the points in terms of values of S and I such that S dot equals 0 and I dot equals 0. So that's what we're doing. The big picture here is we're solving for values of S and I where S dot equals 0 and I dot equals 0 simultaneously. And so one of them was where I equals 0, this disease for equilibrium. And the other is when we have this endemic equilibrium, okay? Here, I is not equal to 0. And here's the trick, and this is a very common trick. Okay, it's a very common trick. If you know I is not equal to 0, you can divide both sides of an equation by 0. So let's go check where this is the case. See it right there? See this? So if I dot equals 0, it means this whole thing equals 0. Eh? If I dot equals 0, this whole thing equals 0. Because I've already handled the case where I equals 0. Here I know I is not equal to 0, so if this thing equals 0, I can divide both sides by I. I don't know what it is, but whatever it is, it's not 0, so I can divide legitimately the thing on the left by it, and the thing on the right, it's 0 divided by whatever I is. As long as it's not 0, that's fine. So it'll still be 0. And then I've got something over here on the left, which doesn't involve I anymore. All it involves is 1 over R. What tau? Thank you. And here this is C times 1 over N times beta times S. So this is 1 over tau, and I can move that over there. So then we have the 1 over tau on the right-hand side, and we have C times beta times S over N on the right-hand side. We multiply through N, and basically you could solve for S. And now you've got S. And then you can plug S into this guy, and you can work to solve for what? Solve for I. The I's have it. That's right. So then you work to solve for I. And that's all laid out here for this particular model. Okay? That's all laid out. So there we go. We know I is not equal to 0, so here's S, and then here we could substitute in. So S dot equals 0 implies this thing equal to 0, which implies this. Notice we've already have S, so we could just substitute in right there for S, and right here for S, right? And we do some algebra, and basically we get this guy then, here I dot equals that. Okay, so here we're sort of successively solving solving for this. Okay. That's what's this is the solution for I, and notice it is contingent. I say this thing has to be non-zero, and then we could solve for R since we solved for S and for I. Okay. So that's the solution for that. And I posted that earlier. I also took pictures of the board, and I also checked it. I checked it at the end. Does S plus I plus R equals N? I took what I solved for and I add them together, and I saw that they equaled N, and life was good. Okay? Okay. So that's that solution. Okay, questions about that? I could also solve for the gophers. If you want me to solve for gophers. Solve for gophers. Okay. What other questions can I answer first, though? So big picture, when you're going to solve that, tell me. You write down the equations. You look to make sure each flow is represented inflow and outflow, assuming that it doesn't flow out to, to a cloud. So assuming it's going from a stalk to a stalk, you could see it flow into one stalk, flow out to the other. Great. Then, so you write down those equations. Then you go and you note any situations where they all sum up to a number, in which case you only got to deal with two of them. Okay, that's great. And then what you're going to do is you're going to say, okay, I want to solve so that the rates of change, like S dot and I dot, equal 0. And you're going to say, I'm going to solve for S and for I when these things equal 0. S dot equals 0, or ds dt equals 0, and di dt equals 0. That's the same as saying S dot equals 0, I dot equals 0. So you're going to solve for the S and I such that that will be the case. And that is, you're solving for those things in terms of the parameters. So whatever the values of the parameters are, you're going to be solving for that. So here you're solving for S and for S, for example, in terms of these parameters. Yeah? And then in order to do that, you're often going to be able to break it up into two cases, like one where I equals 0. That's going to correspond to the disease-free equilibrium. Here, I equals 0. That's the definition of this. I equals 0. And then there's going to be a case where I does not equal to 0. I equals 0 will allow you to simplify some equation by dividing through by I not equal to 0 will basically,
Vice versa.
Vice versa. I not equal to 0 will allow you to divide through by I equals 0 will be very simple for another reason, because you just plug in I equals 0, and it will make a lot of things 0, and it will leave only a few things which depend on S and allow you to have a value for S. So pretty straightforward thing there, but if you get confused, give me that high level of what you're trying to do. Okay? Good. Should probably note, we have here a situation where S plus I plus R equals 0. What's another case where we might have, so here the total population is constant. People just circulate. What's another case where the total population is constant?
When the amount of people leaving is the amount of percentage.
Yeah, the rate of people coming in is the same as going out. The birth rate is the same as the death rate. Those are very common cases where you're going to be able to make the simplification. Oh, the total population is always going to be the same, so I can get rid of needing to worry about one of those stocks directly, because that stock will be some number, the total population size n, minus the other two stocks. Simplifies your life a lot. Okay? Okay, good. Other questions? So in general, you have two stocks you're solving for. There'll be two equilibria, and often, in these cases, one will be stable and one will be unstable. Okay? Other questions? Yes.
Can you talk just a little bit about the sensitivity and calibration?
Sure. Sure. Okay, I will make some utterances about those. Let me just check here. Do I have some nice slides here? No, infectious, formal, discrete event, individual, okay, methods, no. Okay, alas. Okay, I know it's a good slides. Okay, so let me make some high-level comments on things I think are really important in that area to know. Number one, the goals of each. I talked a lot about how there's common computational mechanisms and so on, but the goals are distinctive. Sensitivity analysis, we're trying to assess the degree to which model outputs are sensitive to, are affected by changes in model parameters. Okay? So as we change model parameters, to what degree is a given model output affected? And in a nonlinear model, often we can have very different sensitivities to different parameters. And even at certain points in state space, certain points of the system, like in equilibrium, the sensitivity will be different from, at some other points where it's not in equilibrium. So we actually can get sort of circumstance varying sensitivity. You should be aware of that. But sensitivity analysis is this attempt to kind of ask how sensitive are the results to changes in this parameter. And often what we do is we just run the whole model with a higher value for that parameter and a lower value for that parameter. We see how much the results differ. So we'll do a whole run with the model parameter's default value and then 10% higher and 10% lower, or 1% higher and 1% lower. And here I'm kind of abstracting over several related issues. There's actually a notion of elasticity analysis, which says, if I raise the value of the parameter by X percent, what's the percent increase in the output of interest at some final model time or what have you? Or I might ask about sort of classic sensitivity analysis where I say if I raise it by 10%, what's the absolute increase in the output of this parameter? But the point is, I'm saying as I flex this parameter, how much of a difference does it make in the output? I also didn't talk much in class about how it does differ for different situations for a nonlinear model, like if it's in equilibrium. And I'm not going to hold you responsible for that. Now, a very important consideration is with stochastic models. Because if the model is stochastic, measuring sensitivity analysis in a naive way with just one run, one realization of the model is going to give misleading results because it may be by chance, by happenstance, it's high, even though it's not very sensitive to that parameter. It's just by the luck of the draw, that run of the model, with the baseline value was low and the run of the model with the alternative value was high. Even though the parameter is not very sensitive, it was just by luck of the stochastics that it was a big difference in the output. So generally speaking, with stochastic models, we have to assess sensitivity analysis, we have to run the model many times over for a given assignment of parameter values. So for the specific set of parameter values, we'll run the model 10 times. And we'll take the average and the results, and we'll compare it to, with an alternative value of the parameter, we'll run it 10 times to take the average of the output, and we'll see how they differ. Okay? So that's sensitivity analysis. Now, There's also a form of sensitivity analysis that's called Monte Carlo sensitivity analysis. Now here, we're not actually increasing the value of the parameter by a specified amount. Rather, we're drawing the value of the parameter from a distribution. So rather than exploring how model output varies for, maybe this is output of the model, for fixed, defined, equally spaced values, say, of a given parameter. Rather, what we're doing is, so that might be, sort of a classic one-way sensitivity analysis. Maybe it looks something like that, or maybe it looks something like this. And often we're just going to focus on the baseline and 10% more, 10% less. Maybe this is the baseline, this is 10% less, 10% more, and we'll sort of assess sensitivity around that. Another thing, though, we might do is we'll impose on the parameter, so this is the value for parameter A, alpha, we'll draw it from a distribution, and we'll see how the output of the model, what's the distribution that's implied for the output of the model. So here we might have output of model, and what we will have is some distribution of possible values for the output of the model, something like that maybe. So here we're imposing a distribution, we're getting out a distribution, okay? And this is called Monte Carlo analysis, after the famous casino in Monaco. So putting in a distribution, so this is a probability distribution, PDF, probability distribution function, and probably density, if this is continuous. And here's also a PDF of the sort of model output. Okay, so this is called Monte Carlo analysis. We can, in general, have what's called multi-way sensitivity analysis, where we might have a grid and we're evaluating each of several points along the grid in a systematic way. Or we might do it in a way that's more clever than that, where it's not all equally spaced, but it's adaptive in some way. But these are all designed to test how does the model output vary with changes in parameter values. Okay? That's sensitivity analysis. Calibration, on the other hand, is rather different in its goals, even though the particular methods it uses have some overlap. Calibration is about trying to adjust model parameters so that the model output most closely matches some typically empirical, some observed data from the world. So we have some data from the world, and we're trying to get the model to accord with it as close as possible by adjusting certain parameter values. So here, it's not so much we're interested in studying model output, it's more that we're interested in achieving a certain model output by manipulating the values of variables. So we're manipulating them with a goal, not just for scientific exploration of how does it vary as we change this, how sensitive is it to this. Rather, we're instead trying to adjust the value of the parameter so that the model output most closely accords with what we observe. And often that's a highly adaptive process where it's discovering better values over time. And the AnyLogic optimization engine, the so-called OptQuest engine, uses a very sophisticated genetic algorithm to try to figure out what values of parameters are yielding the best results and how to find maybe even better values of parameters. And it's exploring in parameter space. So, we might have two parameters, and it's actually exploring, not in a systematic grid typically, but kind of exploring through here, trying to find better sort of values of the parameters, trying to optimize it so that the discrepancy of the model output to the observed value is minimized. Okay? And once again, stochastics makes these more complicated because we'd like to have some reliable measure for a given value of the parameters, how big a discrepancy is there? If we assume that for the parameters, how big a discrepancy is there from the observed data? And if you only make one run in a stochastic model for a given set of given assumption about the parameters, you may by chance get something that really well matches the empirical data. But maybe if you ran it again with a different random number seed, you'd get a much less favorable result. In that case, we're at risk. And so typically during calibration, we'd like to be able to run the model several times at least for a given assumption about the parameters. We'd like to run the model several times over, several realizations, so that we're reasonably confident how good a match it is to the discrepancy. And that's what's going on in any logic when it's trying to minimize the subjective function. It gives you that option with the replications to run the model many times, maybe 5 times, 10 times, 100 times. And for each of those, it's going to take the mean value of the objective and try to minimize that mean value where the mean is taken over the set of realizations. For that set of parameters, it's running maybe 100 times and getting an average discrepancy, and then trying a different set of parameters, running that 100 times, getting an average discrepancy. And it's on a quest. It's trying to smooth out the best value for those parameters, the single best estimate of parameters. And you could think of it, the optimization engine, as kind of exploring a space where it's trying to get to the ground. I can illustrate it best. Maybe we'll do something like this. This will take a little bit of setup, but maybe it'll be worth it. Okay, so here we go. We're trying to find the lowest spot in this room, right? And so maybe we're starting up here, right? And it finds, wow, I'm getting a lot better value for the discrepancy function. It's getting lower and lower. Life is good. This is really great. Oh, okay. Now it can't go any further. Can't get any better going that way. So it's kind of exploring around. Oh, going down here, and now, okay, it's not getting any lower. It's kind of stuck. Now, if this were purely what's called a hill climbing algorithm or a gradient descent, and it got down to sort of a minimum here, it might give up and declare victory. But in general, a smarter algorithm, a global optimization algorithm, will realize, okay, maybe I need to sacrifice a little bit right now to get even better. So maybe it will let it get a little bit worse, and then boom, now it's down to here. And now it's casting around, and it's still not getting better, but it's improving some, and then boom, it gets down to here. And then it's, going around, and then boom, it gets down to the floor, and then, well, it could go through the crack. But it's not always accompanied by audio annotations, but that's the basic mechanism by which it works. And so it needs to be tolerant of some so-called local minima, cases where it can't go down any further right now, and where it actually has to give up some ground in order to have a chance of improving. And these algorithms, therefore, need to balance between what's called exploration, where it's trying new things, and exploitation, where it's just taking advantage of the existing things. Trying to microfine the height within this surface versus trying to explore something further away that might get it to the big game. And this whole balance between exploration and exploitation is one of these challenges which comes up in other types of search as well. But that's what's going on in the optimization algorithm, is it's trying to adjust the values of the parameters where, the height, x might be one parameter, the y and the z might be another parameter. And so it's adjusting those to get to the minimum value of the objective function. Yes.
There's
Al?
a possibility there, like the values that you have
Mhm.
for your like parameter sets,
Yeah.
multiple
Yes.
value sets for your
Yeah.
parameters might
Yes.
match your
Yes.
real world data.
Yes, and
How
so
do you determine which is the best one?
this is a great question. Okay, so these are the sort of topics that I'm planning to cover in a more advanced modeling class next year, but yeah, it's very, very common, for example, that as you go down, you might find that there's no one solution. Let's suppose you're purely optimizing on this. You might come down here and you find there's a long, narrow valley here, where anywhere along this valley, it has different combinations of maybe x and y, but all of them yield roughly the same value for the objective function. There's no real gain one over the other. And so there it's a degenerate problem. You have multiple solutions. It's underdetermined. So there's multiple solutions which satisfy it, adequately. And in those cases, you often are interested in understanding what is the nature of this relationship, any of which is better. You're not interested in an arbitrary one. You're kind of interested in the class of them. And because often that tells you something about the model, that, the model has basically its ambiguous situation. I can explain the data from the world either with, high x but low y, or high y but low x, or anywhere in between. That tells me something about the uncertainty involved. So generally you want to communicate something about that ambiguity. And there's methods with calibration. In fact, in any logic, if you were to run calibration with different random number seeds, you might get different answers for different runs, in which case compiling the result of those and then diagramming out what's going on could be very insightful in terms of understanding what the ambiguities are in the empirical data. Really what that's telling us is our theory of the world is captured in the model, has ambiguity about how it relates, how it can explain the data in the world. We need more information from the world or a more particular theory. But a more sophisticated way of dealing with it yet is to assign a probability distribution to possible parameter values where, each of these is equally probable, but it's much less likely to be a parameter value up here, for example. So we can get out a probability distribution out of something like calibration using a technique known as MCMC. But this allows us to sample from a distribution of parameters. But don't worry about that much. But yes, you put your finger on a very important issue, a very valuable issue, and it's one which has practical implications. Good. Other questions? Questions from the sample exam?
Question 35, please, on the sample exam related to dimensional
Yeah, dimensional analysis. 35?
Yes, please.
Very good. Okay. Dimensional analysis. Yeah. Okay. Good. Yes. Okay. Dimensionless quantity. This is, again, somewhat of a misnomer, i.e. of unit dimension. We also call it unit dimension. So do you have a question about that, or would you like me to comment on that?
Well, because as soon as I read the question, I just like, seeing it's already unit dimensions,
Yeah.
why would it be matter if you change the value of itself? It should not affect others, right? Because you are unit dimension, so
Okay.
like invariant, that's what I'm trying to say.
So something of unit dimension is invariant to units. So the example I gave in class was, for example, the fraction of this tabletop that's occupied by this thing here. It doesn't matter if I measure this tabletop in square meters, this one here, square meters or square feet or square inches or square centimeters. It really doesn't matter because the fraction occupied by this is the same, right? So fractions are a great example of something that's dimensionless. Probabilities, same thing, because it's really the fraction of the coin flips that come up heads, right? So So ladies and gentlemen, when things are dimensionless, they're independent of the units by which we measure things. And so what I was asking here is, if we have a numeric quantity in the model that's dimensionless, how would its numeric value change if we change time units, like from month to years? And the answer is that it would not have to change. So, dimensionless quantities are kind of the natural quantities to describe physical systems. They're quantities which are in some sense privileged because they're independent of our conventions. And in physical sciences, maybe Ryan would have come across it, or Lavi, you. If you look at physical descriptions for example, in characterizing turbulence, there's all these dimensionless quantities that come up. And if there was some alien civilization and it had a very different unit system than ours, we could still be confident that they would understand that has the same intrinsic values because it's independent of our unit systems. It transcends our conventions. And dimensionless quantities are like that. And because the world operates in a way that's independent of our unit systems, it has to be amenable to, it has to be able to be described in dimensionless terms alone. And so it turns out that any model that's dimensionally homogeneous, dimensionally consistent, that doesn't have unit clashes, can be reframed, recharacterized in a way that involves only dimensionless quantities. And by so doing, you may be able to save 2 or 3 parameters out of what it really would have originally described, because it's often more compact how you specify it as such. So one of the advantages for doing dimensional analysis is you can simplify the description of a system. You can take a system which has 5 parameters and bring it down to 2. Or you can take a system that had 10 and bring it down to 5. So you can have a simpler, more parsimonious description. Why would it be advantageous to bring the number of parameters down from 5 to 2? If you were undertaking what sort of processes described over there on that board? Calibration or parameterization. Man, if you could explore a 2-dimensional space rather than a 5-dimensional space, you're really reducing the computational load and making it and enabling a much more thorough exploration. So it can be really valuable. Those are some of the advantages of dimensional analysis. So dimensionless quantities of unit dimension, will not have to change their values as we change from one unit system to another. Okay? Any other questions? I do want you to be able to, to look at something and say, what are the units of it? What are the units associated with it? And I gave a problem in there, that hinges on that. But one of the most important principles is that if you have a stock, and you have a flow into the stock. Oh, please, 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 I beg of you. I beg of you, folks. Remember this principle. So X is of unit U. What are the units associated with the flow? U over some time, tau. And what that means is if you have a time constant, tau, whose units are dimensions or time. It's dimension time. This is dimension U. This is dimension U over T. This is dimension dimension u, okay? And this is a first order type of arrangement, so this depends on x. This needs to be x over tau, not x times tau. Right? There could be a constant out in front, a dimensionless constant. But basically, use this to distinguish between the cases. If you can't remember, do I divide by a time or multiply by it? You got to divide by a time if to make, you've got, whatever you do, you need to make the dimensions of the flow be the dimensions of the stalk divided by time. Now, if I have a hazard rate, a chance per unit time, what are the dimensions associated with that? 1 over time. This is 1 over time. Probability per unit time. Probability here is dimensionless. It's a unit dimension. Okay. Fraction of number of heads over total number of coin flips. It's coin flips over coin flips, therefore they cancel. Okay. So if you have a hazard rate, chance per unit time to advance, it's that times the stalk to get something of dimension u over t. If you could remember that, boy, that would be great. Boy, that would be great. Okay. Every year I get at least a few students who mess up on that. And it doesn't quite cause me to cry, but it makes me rue the fact that I didn't emphasize it. And every year I give this exam review. And every year I think I've given away the secrets. And every year I realize I haven't. A few days later. Okay, so what other questions can I answer?
I wasn't clear on question 39.
Okay.
Sorry, at the end there it just said, please indicate whether the state space would be totally filled, and I wasn't sure what.
Oh yeah. Thank you, Janelle. Okay, this relates to the so-called state space methods. Okay, and there's a couple things I'm going to ask you to know about here. The basic idea of a state space plot. What form the axis of a state space plot? When you run a model, what does it look like in a state space plot? And what does a fixed point look like in a state space plot? In fact, I've been plotting them here. Right? These are state space depictions of things. But I want you to know, like, what are the dimensions of a state space plot? What is the dimension? What are the coordinates of a state space plot? What is it that's along each axis of a state space plot?
The independent variables.
Yeah, the independent variables of a system. Good. Or the nominal variables of the system. And as we'll see, if they're not all independent, we'll see structure within it that will indicate that. What does a trajectory look like in state space? Well, it looks something like this, or it looks something like this. Here we're kind of starting the model off, and it's going around and it's circling into this attractor. That's one of these guys here. Okay. So here, this is a trajectory. Time is flowing along here, but it's kind of implicit in it. It's kind of parameterized by time. Okay, it's looping around. This is another example of a trajectory in state space. Here we plotted it out, and it got sucked in to this equilibrium. If it had just been a little bit over the line, it could have gone this way and gone up and gotten sucked into a different equilibrium. So that's an example of a trajectory in state space. And a fixed point will look like this, for example, is indicating a fixed point. It's a point of stasis. It's not changing. The flow lines here are basically all, at that point there's no flow, there's no change, and often the flow lines will be pointing towards it or away from it, around it. Okay, flow lines. Here are some flow lines here. How do we calculate those flow lines? These are little arrows. I know it's hard to see, but there's little arrows pointing down here, pointing this way here, pointing up to the upper left here rather, pointing this way horizontally here. How do we calculate the flow line? Yeah, we take the derivative of x and the derivative of y. If the derivative of x at a certain point is positive and the derivative of y is positive, where will that flow line point roughly? Well, derivative of x is positive, derivative of y is positive. It'll point somewhere up here, maybe that way, but up in this quadrant. If derivative of x is negative and derivative of y is positive, where will it point? Well, it'll be kind of like this, right? X is negative, y is positive. And similarly for y negative. So basically it indicates the quadrant that it's in. And you could figure out the angle from the tangent of the two, or the arctangent of the two. But the basic deal is that these flow lines are calculated based on the derivatives at a certain point. So at this point in state space, we can, well, how do we calculate the derivatives at that place?
Plug in the value.
You just plug in S is this, I is that, you plug it in to your equations, to this sort of thing, you plug in, S is this, I is that, and you figure out is S dot positive or negative, right? And same thing with that. So that's how we do that. Okay. Now this gets to Janelle's question, ladies and gentlemen. So I asked, does it fill the state space? Okay. So here we're going to go look at illustration 2. Here's illustration 2 back here. So if we diagram out this in state space at a nominal level, what we're going to get is be hard for you folks to see. Okay, opportunity cost. Okay, so here we go. So if I wanted to draw the state space, what would the dimensions of the state space be if I'm just dealing with it at a naive level? Yeah, there'll be 3 of them. And so here we go. So this is sort of trying to represent this in 3 space. Susceptible, infected, and recovered. So this is kind of not, it kind of goes like that, right? Kind of back going into the board, kind of. This is a 3-dimensional space, and that's sort of the state space. And as the model runs here, it's going to etch out a trajectory. The deal here is that if we think about it in that context, here there's a certain invariant that holds. We talked about it before. What's the invariant that holds, that links together susceptible, infective, and recovered? Yeah, constant population size. So S plus I plus R equals N. And what that's going to mean is that, although nominally it's in 3 dimensions, here's the trajectory. If you look at it from the right angle, it's going to be a flat line. And why is that? Well, it's all going to play out on a plane where S plus I plus R equals N. Meaning if we specify S and I, we can immediately get get R back from that. And so the nominal dimension here is 3 dimensions, but it's going to actually play out all on a plane where basically that plane is going to maintain the invariant that at any point in this plane, S plus I plus R equals N. And so it's not going to fill up. If you have a given size of the population, it's not going to, for example, ever go to the point where, you know, Si and R are 0, for example. It's not going to reach areas where this is not the case. Si and R are not equal to N. And that's going to mean it only is limited to a plane in space here, rather than occupying the entire space. So this is what will be called the intrinsic dimensionality, or just defines the intrinsic dimensionality of the space here. That it's within a subspace of this. It's not occupying the entire space. It's only occupying a 2-dimensional sample of this space. Yeah.
What you're asking is essentially, is it possible for the values
Yeah.
to occur on? Okay.
Yeah, exactly. Yeah, to be honest, that was one of the questions I put in late in the game, and you're good to ask. The wording of it is not quite right, but what I'm trying to ask is it possible for the trajectories to go anywhere in the space? Maybe that would be a better way to say it.
Yeah, that helps a lot.
Is it possible for them to travel anywhere within this entire space? Yeah. Okay. Other questions? Now, there was one other thing related to this that I wanted to just mention, and that, you know, I gave this lecture on this portion, but the entangled nature of this. The idea here is that that within these nonlinear models, data from one type of observation about the model can sometimes even clue you in to the nature of that state space. In other words, you can visualize the entire state space using data from just one type of output, because the system is so coupled that one piece of information repeated, say the number of gophers, can tell you all the information you need to know about the number of coyotes over time and how that changes. Okay? Or information on the observations of the number of infected people could tell you about how many people are recovered and susceptible right now. So you get these kind of entangled systems where just a single observation over time from one part of the system can tell you about the entire system. It can let you probe what's going on in the entire system over time. And that's a notion of embedding, it's called, the embedded nature of the system, okay, embedding. So that was something we talked about with state space methods, okay. Okay, other questions? Here's some broad topics. We haven't talked about networks. We haven't talked today about networks. Networks are going to be part of this. In some ways, I'd feel I'm doing you a disservice unless I make some utterance on networks. So utter I will. So what type of networks did we discuss in this course? Ring lattice. So what's a ring lattice network?
Local network.
Very local. Almost essentially one-dimensional. Right? It loops around, but it's essentially one-dimensional. Its intrinsic dimensionality is one. It's a big sort of long loop. And how do contagion processes spread on a ring lattice network?
Die down quickly.
They tend to die down quickly because you can get these kind of firewalls set up where, if it's blocked, that's the only one way to get to it. There's only one way through, and if it's blocked, that's it. Okay, so ring lattice networks tend to be slow to propagate. Okay, give me another type of network. Poisson random network. In a way, that's the flip opposite. That's the complete opposite of a ring lattice. Why do I say that? It's global. Yeah, ring lattice. Position is everything. Who I'm connected with is completely defined by my position. I'm connected only with neighbors on my left and right, or two to the left, two to the right, or whatever. Very local. My position defines anything. In a Poisson random network, I'm connected to anyone, regardless of my position or their position. Any two nodes has equal likelihood of being connected wherever its position has to be in the network. In terms of the ordering of nodes or whatever, two nodes are equally likely to be connected willy-nilly. Great. What's something that's in between? Small world. Okay, so let's talk about each of those additional ones. So for a Poisson random network, what's the implication for contagion? It's almost like system dynamics. System dynamics, these equations, ladies and gentlemen, these equations assume what's called random mixing. I have seen contacts with anyone in the population, and to figure out what fraction of them are infective, I'm looking at what fraction of the whole population is infective, I over n. That's a very global sense of mixing. We call it, in fact, random mixing. And Poisson random network is very much like that. Even though it's with fixed people, they can be anywhere across the network. So it's very similar. And as a result, the infection can jump across the network very easily. Probably my connections are all across the network. There's no privilege to local connections. That's good. How about that intermediate type, the small world?
It's like a ring lattice with a small number of random connections.
Small number of random connections. In the dynamics we see in contagion there, spread of a rumor, or spread of an innovation, or spread of a pathogen, they tend to be much, much, much quicker than a ring lattice, because just a few global connections make a huge difference. It could just leap across the network. You don't have that bottleneck, that bulwark effect, or bulkhead effect, where if a path is blocked, that's it. You've got many paths across the network. So just a few connections that are global can make a huge difference in terms of the dynamics. Okay, what other types of networks did we discuss? Scale-free. And give me a couple things about a scale-free network that are distinctive.
There are a few people with a lot of connections.
Few people with a lot of connections. A few hubs with lots of connections. Good. How about something else? Power law distribution in what distribution? In the distribution of the number of connections per person. So if I have a probability of having n connections versus probability of having 2n connections, the ratio of those probabilities, probability of n, having n connections, or let's call it k connections, versus probability of 2k connections, that ratio is the same regardless of what? Regardless of, of k. K could be 1, I'm comparing the probability of having 1 versus 2, or it could be 100 versus 200. So if I'm twice as likely to have 1 connection as 2 connections, the same thing is true as twice as likely to have 100 compared to 200 connections. And what this leads to is a situation where you have if you plot out the log of k here, log of the number of connections, and the log of p of k, what do you get? Straight line. Straight line, ladies and gentlemen. And what this generally means is there's going to be some people out here with a massive number of connections. Think of them as the salespeople who go around the globe and just meet hundreds of people a day or whatever. It's just some people are going to have a massive number of connections, but most people are going to have a fairly small number. A small fraction is going to have a massive number, but it's a pretty heavy tail, actually. Now, why is that of interest? Because the number of connections matters. In a contagion process, why is the number of connections so important? Give me 2 reasons. If there's someone with a lot of connections, what are 2 distinguishing features about them?
They can spread the disease really fast and get it really fast.
Yeah, they can both get it really easily and spread it really quickly. And that could be true for a disease. It could be true for a rumor. It could be true for an innovation. It's not necessarily good or bad. It's just that these people with lots of connections are disproportionately influential. They're disproportionately influential. And, for the case of a disease, often it's the people with large number of connections that keep you would think from the analysis that R0 should be less than 1, that the disease should be gone, it should be dying out. Most people, if you look at the average person in the population, based on their average number of connections and their chance of passing it on and how long they have the illness, you think about it, the contacts per day that they have, if it's all with susceptibles, it's that many contacts per day with susceptibles, and you multiply that by beta, the chance of transmitting it to one of those susceptibles. So now you've got C times beta. That's the number of people to whom they might transmit each day, times duration, how long they have it. C times beta times D or delta or however you denote the duration. That might be less than 1 for the average, based on the population averages. And so you might think the disease will die out, but it doesn't. It doesn't, because there are these disproportionately important people with lots of connections. And they are the tail that wags the dog. They're going to prevent that bug from dying out. They're going to keep it alive, even though you might think from an aggregate analysis it can't stay alive. Based on the population averages, you're wrong, because those people out here are disproportionately important. The folks out there have this extra power. They may be 1% of the population, but they determine whether or not the infection dies out or lives. So scale-free networks are very important, and they're of great interest right now in many different domains, human, technologic, etc. Scale-free networks. And there's also a distance-based network, a network in 2 dimensions. How does that differ? A distance-based network. What are its dynamics like?
It only connects the people within a certain distance.
Good. And if we have a contagion process on that, how does it compare to, let's say, a scale-free or small or a ring or a Poisson random?
Most likely like ring lattice.
Yeah, it's kind of like ring lattice, but in 2 dimensions. It's very localized. So once again, you can get blockers who stop it from spreading. So you prevent it from percolating over. And it's really, ladies and gentlemen, not until enough susceptibles, for example, build up that they form bridges across the network, boom, then you can get the infection spreading. As long as you have a ring, sort of a distance-based network, as long as there's no bridges easily to other areas of the network because maybe people are not susceptible, you won't get the infection able to spread. Okay? Good. So networks are important, ladies and gentlemen, and they're of great interest both for their structure and their dynamics. Good. Decision analysis. What are the three types of nodes of a decision tree? Terminal node, decision node, and an event node. Okay. Okay. Tell me, if we are going to put together a decision tree and a simulation model, where does the result of the simulation model go in the decision tree? In the terminal node. Good. And what process do we do to figure out from the decision tree what decision is best at each decision point, or to determine the best decision rule? We do a rollback. And what does that involve? A rollback, it's called backwards induction. It's essentially a type of dynamic programming. What does that involve?
Going back through the end to the beginning to see where
Good.
and doing calculations to see where the most optimal calculation.
Good. So with a decision tree, write it with time from left to right. Right? And here we might have decision nodes and so on. And we have terminal nodes down here. With a rollback, we're doing it bottom up from these terminal nodes, right? Up to the root. For a terminal node, what are we doing? What's the rule for how we calculate the value of a terminal node? It's a bit of a trick question. Well, it's just given to us, that number, like taken from the simulation model. Okay, for a decision rule, what is the value of that, or decision node rather? What's the value of that decision node?
It depends on what we're trying to maximize or minimize, but we would take the better value of the two.
We take the better value. Whatever value is best, we take that. So again, we're calculating from the leaf nodes up, and so by the time we're doing the decision node, we have the value of each of its children, however many children it is. We're just choosing the best one. Okay? How about for a chance node? Well, okay.
Take the expected value.
We take the expected value. A chance node does represent an uncertain occurrence, but because we don't know which one will occur, we're kind of hedging our bets by considering all possibilities. And some of the possibilities may be good, some may be bad. We don't know which is going to get. We're calculating its outcome as the expected value of the outcomes of all the children. So if one of its children is with probability 0.9, and let's call this V1, and another children is 0.1 and V1 and 0.9 with V2, then the value associated with this event node, we'll call it event node 1, P of E1 equals 0.1 times V1 plus 0.9 times V2. Right? It's the expected value. Remember, with the expected value, you're basically taking the probability times the value of x for that case, and you're summing it up over all possible eventualities. Good. So that's what we're doing when we're doing rollback. And what's the point of rollback? What do we get out of rollback? The best decisions, or to sharpen that a little bit, the best decision rule. And what do I mean by a decision rule? A strategy for making decisions that specifies what to do under any possible eventuality. If this happens, do that. if this other thing happens, do this. Generally, it's a contingent statement. It's fairly rare that a static decision rule is best. Just do this under all circumstances. Rather, it typically depends on what has happened. Under this situation, you will do this. Under that situation, you'll do that. That's an adaptive decision rule that has those contingencies. And that's what we're going to get out. What does a decision rule look like in a tree like that?
A path through it.
Okay, there's a path, but a strictly linear path here, like this guy, is actually a scenario. What does a decision rule look like that's different?
Path for each.
Yeah, there's a path. So when we have an event node, we're not sure what's going to happen. So we have to have a contingency plan, a strategy for handling any possible outcome of this. Decision, we can choose what to do. So we say, if we get there, we're going to do this. Fine. We don't have to worry about its other paths. But if this passes through an event node, we have to be able to handle any possible eventuality. So it might be something like this. If this happens, we'll do this. If that happens, we'll do that. We'll take that branch. So this would be, and maybe this is a decision node. So we don't have to worry about that because we'll just choose not to do it. But in this decision rule. But if we come here, and this happens, we'll undertake this choice, otherwise that choice. So for every reachable decision point, we have a strategy. And basically it tells us under any possible eventuality what we'll do. Does that make sense? It's a decision rule. It's a strategy for handling things. Good. So a simulation model puts in values for the terminal nodes. What, if anything, does this decision tree have to tell the simulation model?
Changes in parameters, possibly.
Yeah, exactly. So, if the simulation model is going to simulate this scenario or that one, it needs to know what choices were made on the path to it and what events happened. So it needs to tell the simulation model, hey, I need to calculate this outcome. You made that decision at time t1. This event occurred at time t2, and this decision was made at time t3. Go figure the consequences, and the simulation model will run and give a value for this terminal node. So the decision tree here is responsible for sort of characterizing policy space, the set of possible choices and uncertainties over time, and the consequences. And the simulation model is responsible for calculating the results of particular scenarios. Decision trees and simulation models together help us deal with dynamically complex dynamic decision problems that involve choices under unfolding uncertainty with where there are consequences as a result. So here we have this unfolding uncertainty as time goes on, and we're making choices in response to that. Good. Talked a little bit about metalinguistic abstraction. Nothing fancy here, but you should know what the term means. Basically, as computer scientists, we can choose not only how to frame a problem, but in what language to frame it. And we can build our own languages to frame them. And here in this class, we've looked at 3 languages for describing complex systems: system dynamics, agent-based modeling, and discrete event modeling. And by picking the right language for the job, by abstracting, by using the right language, not just creating functions, but using the right language, and sometimes creating the right language, often we can enable very powerful types of analysis. That's that's good. Hybrid modeling have presented 5 types of hybrid models, including those that combine DES and ABM, those combined system dynamics and ABM. These are fruitful different patterns. The biggest point there is that these days it's not a matter of picking just one way of describing it, but picking for some projects which portion of your model you wish to be in what approach for describing it. I'm not going to be asking much about the particulars of any logic. For example, Rowan and Jared did a great little project on using a different, they created their own little simulation framework in Python, which is great. I'm not going to be testing you on, the exact types of supported mechanisms within AnyLogic in detail, okay? AnyLogic is a useful tool, but I'm not going to be leaning on that as an important part of this exam. I think those are most of the topics that I'm talking about. There's a notion of pattern-oriented modeling, sort of modeling to explain patterns we see in the world, and we want a model that will automatically generate patterns. There are some, like Josh Epstein at Johns Hopkins, who argue that generative explanations are an important feature of science, and that we don't really truly understand a phenomenon unless we can generate it without presupposing it. And pattern-oriented modeling is sort of this notion that we want our models to reproduce automatically certain patterns we see from the world. State space methods, we've talked about those. Decision trees and decision rules, causal loop diagrams. Feedbacks, positive feedbacks can be positive or negative. Give me a case where people want positive feedbacks. They'd like to see positive feedbacks.
Interesting. Appreciate.
Yeah. So you'd be interested in having, your new product, for example,
Well,
I meant
like money.
go viral. Oh, interest. Sure. Like interest in a bank.
Yeah.
Accruing of interest. Okay, fair enough. Yeah, I like that. So that's a case where people are seeking positive feedback. Reinforcing feedback is also a dominant feature of how companies often want to grow, right? Skip the Dishes wanted log linear growth and got it, right? They just got bought out for $110 million last week or the week before. And they were trying to grow like at least double their size every year. They told me, I think, that they'd be really disappointed if they can only double every year. And so this form of sort of reinforcing feedback is viewed as desirable there in many cases. On the other hand, it can be undesirable. You can get these vicious cycles where, things compound. We get snowballing effects where, one insult leads to another and you just get to a worse and worse situation. Addictions, cases where someone starts off in a direction that they think they can just get into a bit, and they get sucked into it in a more and more strong way and find it harder to break out. We talk about things like the cycle of poverty. Balancing feedbacks are similarly ambiguous in their consequences. We can get lock-in effects where we are trapped in a certain situation and we can't escape easily, where we have trouble maneuvering because when we try to take action, it pushes back against us. But on the other hand, we can get resiliency, cases where a system bounces back in a very helpful way. So both positive and negative feedbacks can be viewed as either good or bad. The name positive and negative is not normative. it has to do with polarity associated with them. We talked about first order delays. You should really understand how to phrase a first order delay. Ladies and gentlemen, you remember we could have this phrased as a chance per unit time of transitioning, in which case the value of the flow will be that chance per unit time times the value of a stock, or it can be the average amount of time that you spend in the stock, in which case the flow is what? People over that average amount of time, because the units of the flow have to equal the units of the stock divided by time. Okay, this is one way, but there's another big way that I asked you to know about these. And I asked you to do a little take-home exercise at one point related to this. And that is what? Does anyone remember? Another way to phrase a first order delay. So this eraser is dysfunctional. It exhibits dysfunction. It exhibits extra degrees of freedom. Okay. So ladies and gentlemen, first order delay. I alpha, which is some value per unit of time, x. What's the formula for this guy here? Alpha x. What's the average amount of time in x? 1 over alpha. 1 over alpha. So, consequently, completely the same mathematics. We could replace this as tau and make this x over tau, and tau equals 1 over alpha. Alpha equals 1 over tau. We can phrase it either way, right? Okay, great. Now, this is one way to phrase these. Average amount of time there. What is the number of people in this? If x0 people start off in the stock, how many people remain after a certain amount of time t?
The average value, like multiplied by t.
Well, okay, so it's the initial value.
Minus, sorry, yeah.
It's the initial value times what? What's the probability that each person remains in there?
Alpha. 1 minus alpha. 1 minus alpha.
Glad I asked. Glad I asked.
Is it an exponential?
Yes, it's an exponential. It's a declining exponential.
Use the power of alpha over tau.
Okay. Getting close. Okay, is that probability going up or down over time?
It's
Minus. I like a minus. And t, it's going down with t, right? And then tau. Or, phrased in terms of alpha, x0 times e to the minus alpha t. This is the probability that a given of these persons will remain there after time t. Now, if we consider that person who's there at time t, what's their chance of leaving? What's their chance per unit time of leaving after time t? Well, I'll phrase it another way. If they've just entered, they haven't been there long at all, or they've been there for a long time, does their chance of leaving in the next month change?
No.
No, it's exactly the same chance. I'll leave in the next month, regardless of whether they've been there 0 months or 100 months. Contingent on them still being there, the chance of leaving in the next month is the same. Are they more likely? Are they more likely to have left in the first month than in later months? Than in the first month than, let's say, the 100th month?
Yes.
Yes, they're more likely to have left during that time. Their chance of leaving that first month. We know that they were there till that month, so their chance of leaving in that first month is much higher. For a 100th month, they'd have to not left all those previous months. But given that they're still in there, the chance of leaving in the next month is the same. But this describes, this is the probability that they have remained there till now, and this is the original number that were there. So this times this is the number that are still there after time t. Okay, so that's a pretty important relationship. Pretty important relationship. And it turns out you can do the math and find out that the average time they remain there is 1 over alpha or equal to tau. Okay, this is one way to phrase these, but there's another way that is also mathematically identical. Ladies and gentlemen, first of all, what's the equilibrium value of this? What is the value of x at which it will no longer be changing? At equilibrium, what has to be the case? For it to be an equilibrium, a stock to be an equilibrium, what has to be the case?
Derivative is 0.
Derivative is 0, which means what about the inflows and outflows? They are equal. So I equals x over tau. And what is the value of the stock at equilibrium? Yes, which implies that x equals I tau, or phrased in terms of alpha, I over alpha. That's the value of x at which will be in equilibrium. Agreed? Okay, now, I would tell you and I know I'm keeping you over, but this is a worthwhile discussion. Okay? So I can rephrase this in a mathematically identical way using one flow in. Does anyone remember how we did that? We phrased it in terms of a... Yeah, you got the right idea. Got the right idea. There's a thing called a target.
Oh, yeah.
Yeah, there's a target. So now we're still going to have tau, but tau will be written over here. There's only one flow. We're going to have tau coming in here. This is going to involve, ladies and gentlemen, x tau, but it's also going to involve something called the target value, the indicated value, the value to which it wants to go. The stock wants to go to that value. And what is that value going to be? Levy got it. I tau. That's equal to I tau. This is kind of the target value. And what we're going to do to sort of help you understand the formula for this, I'm going to write it this way. I'm going to talk about a gap here. And rather than drawing this directly to there, I'm going to talk about it drawing here. Here's a gap, okay? And the gap equals...
I tau minus x.
Okay, good. So it's the target, which is I tau, minus x, okay? So the bigger this gap is, the more it's going to be flowing into x. If there's a huge gap, if the target is hugely larger than x, lots is going to flow into x, just like that. If target equals x, nothing's going to flow into x. If target is less than x, if target is less than x, what's going to happen?
Negative inflow?
Yeah, it's going to be flowing out. In fact, it's going to be working to reduce x, okay? So if x is greater than the target, gap is going to be negative, it's going to be flowing out. So what is the formula for this in terms of the gap? Well, it's just going to be the gap
over
over
time.
tau. So gap and target, these are just kind of nice names for these things, although often we will talk about this being the target value. Really, it's the value, the natural value towards which x is going to go, because it's
Equilibrium.
it's the equilibrium value. This is going to be, we could phrase it as I tau, this is the target here, right? Minus x over tau. Now, I would argue that this is the same mathematically as that. Let's show it. dx dt here equals what? The top one. dx dt equals I minus what? X over tau. Good. Okay, let's write it down for this lower one. dx dt equals what? This is the value of the flow, so what do I put on the right hand here?
Same thing.
Yeah, I tau minus x over tau. Simplifying, I get what? I minus x over tau. Does this look familiar? This is the exact same thing. We've just reformulated the system from our perspective. Do we want to think of this as kind of a flow in, and the outflow is just a delayed version of the inflow? It's just kind of following the inflow with a certain delay, a first order delay. So if the inflow is low and then goes high suddenly, the outflow will be low, and then it will adjust to its new high value. That's kind of the perspective of the top one. The perspective of this guy here is that x is trying to follow a target. It's trying to reach an indicated value that's told to it. It's maybe this is the world, the sort of the situation in the world, and this is our perception of the world. And it takes this gap between our perception and the world to help us realize we have to adjust our perception, and accordingly we follow the nature of things in the world to sort of adjust our perception to better record with that. So this is kind of target following. Here, basically the value of x. So at the top one, we think of it as the value of the outflow is following the value of the inflow. The bottom one, we think of it, the value of x is following the value of target with some delay. But either one, it's just one is the alternative of another, because after all, the outflow is just the value of the stock divided by tau, or tau is just the value of the outflow, or the stock is the value of the outflow times tau. So we can think of it either way. This was another way of framing the same basic problem, for which you will be responsible. Okay, so this is a good thing to rehearse. If you're not already comfortable with it, this is another way of framing the same system as a first order delay. It's the same first order delay, it's just reframed in terms of following a target, the stock following a target rather than the outflow following the inflow. Good or not? Okay. Good. Good. Excellent. Excellent. What sort of tipping points are there? Where do we see a tipping point? Well, if we don't have a large enough rate of contact, or we don't have large enough beta, or we don't have a large enough duration of infection, what can happen? The infection can go from remaining endemic to the population to disappearing. Could just, instead of spreading, it just peters out, goes away. That's an example of a tipping point, ladies and gentlemen. Okay, and that's an important phenomenon. Discrete event modeling. Modeling, so they're responsible for knowing. It characterizes structured work throughs. It characterizes situations where we have entities, kind of like agents, but often treated more passively, flowing through structured workflows, where their progress through those workflows is contingent upon availability of resources. Often we're interested in also representing spatial constraints. We're interested often in knowing what is the impact of extra levels of resources on the throughput of the system, how many people per unit time flow through. Or we're interested in understanding the impact of that sort of resource availability, how long people spend waiting, how the entities spend waiting. We're also often representing space. Why do we represent space in a discrete event model?
To show how it affects wait times.
Yes. And why does showing space in those models, why is it important for waiting times?
Because there could be congestion with movement. There could be like the length of the movement, like how long it takes to get from one area to the other, how fast things move.
Yeah.
Changes in movement.
That's right. Good. So we endogenize movement. Fancy term. What's the difference in exogenous thing and endogenous thing? What are the three divisions we often divide things into?
Ignored quantities, endogenous quantities, exogenous.
Good. And what's the difference in exogenous versus endogenous? Both are in the model, but what's the difference between them?
Exogenous is hard coded, and endogenous is given by the model at runtime.
Yeah. So to put it in a pithy way, exogenous things we tell to the model. They're pre-specified. That doesn't mean they're necessarily constant or fixed in a constant sense. They may be pre-specified to change in this way over time, but it's all pre-specified. Endogenous, so exogenous, we tell the model what to assume. Endogenous things, the model tells us what is generated. And in discrete event modeling, often we endogenize space, movement times. So what I mean by that is the model is telling us how long people are spending moving, and by implication, that affects their ability to take patients or to assemble the car, what have you. So that allows us to ask, for example, how does the placement of a resource or availability of a resource spatially end up affecting the flow, the throughput of cars through the factory? If this worker has to go retrieve these tools from this area of the factory under these situations, if there's a defect in this, they have to go get them and fix them. Or if a doctor has to take a patient to this type of this area of the procedure rooms, that are further away, how does that affect how many patients can be handled in the emergency room, in an hour? So endogenizing space is really quite helpful for understanding flow, waiting times, and the level of utilization also of resources, like what fraction of the time a worker is busy working on a vehicle, or a doctor is busy seeing patients, or what have you. What fraction of the time the rooms are filled, or the x-ray machine is being used, or what have you. So, ladies and gentlemen, being able to endogenize movement is helpful within these models. We have, when resources are not available in discrete event models, what happens? You people or the entities get into what? Queues. Into queues. Okay, good. Trade-off between modeling types. System dynamics focuses on feedbacks and accumulations. It supports qualitative and quantitative methods. Supports rich mathematical analysis. It's often really quick to run. Feedback-centric. Really nice for characterizing regulatory systems. Systems where there's feedbacks involved in the processing. Agent-based modeling captures interactions between individual population members, can capture individual histories and trajectories, including things we might want to do with a certain person based on their history that are different based on that history. It can represent network connections and kind of spatial and hierarchical context. And you can really richly capture heterogeneity in a way you can't with an aggregate model. With an aggregate model, if we want to distinguish males and females, we double the size of the model. If we want to do so with an agent-based model, we add a parameter which has a very much smaller impact on the size or running time of the model. By contrast, in agent-based models, if we double the population size, it will take more time. But in a system dynamics model, it's just calculating using bigger numbers. It doesn't really change the size. The running time. Discrete event simulation. Here we simulate the flow of individuals through these processes, capturing resource use. It's exquisitely expressive for describing passing of entities through structured flows, where they queue based on resource unavailability and progress is based on resource unavailability, and where we endogenize space and often resource availability. Okay, good. Ladies and gentlemen, I think we are done. And as I say, every year, I think that I've given away the ship, and this year I feel it keenly. Those who are in the room are I think, going to benefit a lot from this discussion. I hope. Okay? But tomorrow morning, we shall see. So it's a pleasure to have you here. Thank you for your extra time. I'm going to take pictures of the board, and as I am wont, I will post them to the site, and I will release this recording before I leave campus this evening. So thank you very much. Best of luck in your final studying, and I will look forward to seeing you early tomorrow morning. What's up? No, I'm gonna stop recording. So.